Kitty cat, watch out. Alrighty, gang, welcome back to pre-calculus MAC 1140. Today we are going to start on a new sort of portion of the class. Instead of talking about graphing functions or analyzing graphs, anything like that, we're going to start talking about a new sort of algebra, linear algebra it's called, which is more exciting than it sounds at face value, I promise. First, I've noticed the zoom settings here are getting a little wonky. Yes, I apologize for the spotlight there. Let's do it like that. There we go. And then, okay. Yeah, so as promised, today we're going to start talking about systems of equations and matrices, which is one of the last big important parts of this course. There we go. All right, you guys don't need to see my breakfast, but I don't need to see mathematics. Let's get the pedal card up and you can start moving on. All right. There we go. So this is MAC 1140 section OR1, which is today is, was it 22nd, is it? Yeah, 22nd. It's 11:22. What are we doing today? Systems. Linear equations. And matrices. I don't think we'll actually introduce matrices today. We might, depending on how quickly we move through this. I'm going to try to feel out your guys' comfort and familiarity with the material, because kind of how much time we need to spend talking about systems before we can get into matrices depends on how comfortable you are with systems. So, let's see. Yeah, 6, 10, multiple variables, and then 10. Okay. Make sure you get the section numbers right. This is 10.1 and 2. And this is 10. All right. So I know you can't get through high school, even middle school these days, without encountering a linear system, but I nevertheless have to define them for you. This is hard to read. It's 10.1 and 2. Real quick, I guess, before we get into this, if you missed exam 3, the makeup for exam 3 is today. My office hours. All right, so if you missed the test for whatever reason, doesn't matter to me. You don't need a doctor's note. I don't need an excuse. You guys know how this works. Just come to the office hour today during the makeup session so I can unlock the makeup version for you and get you in and take that test today. This is the only makeup session for this test, so this is our last chance. All right, so systems, linear systems. I'm combining 10.1 and 10.2 because 10.1 is linear systems with 2 variables and 10.2 is linear systems with more than 2 variables, and really it's the same shit. So what is a linear system? Well, a system of equations in general, let's get this out of the way. A system of equations is a collection of equations meant to be solved simultaneously. Probably misspelling the word simultaneously there. Don't worry about it, not an English class. You know what I mean. So a system of equations is just a set of equations, maybe 4 equations and 5 variables, something like that, where you're meant to find the values of the variables that make all of the equations true at the same time. Oh, there's a question in the chat there, when our next exam is going to be. Yeah, the last midterm I will most likely be on the last day of class, which for you guys is going to be December 2nd. Let's see here, December 1st. So our last test, which is the test on systems, is going to be a week from this Wednesday. It's a short little section. Okay. Okay. I love you. All right. Sorry, I gotta get the fucking cat out of here. Okay, go. Okay, we call a system linear call a system of equations linear if every equation is a linear equation. And we've talked about linear versus nonlinear things way back at the start of the term. Linear means all variables occur upstairs only to the power of 1. Right, so no variables under radicals, no variables downstairs in fractions, no x squared, x cubed, or anything like that. Certainly no e to the x. Linear equations. So a system of equations is a bunch of equations meant to be solved simultaneously. And a system is called linear if every equation is linear, meaning all the variables occur upstairs and only to the power of 1. All right. This is a linear system. It has 2 equations and 2 unknowns or variables. This is also a linear system. This one has 3 equations and 3 unknowns. And when we write linear systems, we always write them in this way, where each column kind of represents one variable. So here, the first column of this array is all the x's. The second column of this array is all the y's. And the third column of this array is all the z's. So we write them in order with all the like terms combined so that you can kind of see where all the x's are, all the y's are, all the z's are. This first equation, or sorry, this first system, I would call a 2x2 system. That's two equations. And two unknowns. This guy I would call a 3x3 system because it's got three equations and three unknowns. Show you a couple more examples here. Show you a nonlinear system to show you what I mean. Before that, let's look at an underdetermined system. Is this system linear?
Yes.
Very good. This is a linear system. Every variable occurs upstairs and only to the power of 1. Don't have any 1 over x's or e to the z's or square roots of y. These are linear equations. These are linear equations. So this is a linear system. It has two equations. And here we have 1, 2, 3 variables, 3 unknowns. So if I wanted to use that same sort of terminology to describe it that I was using in the previous page, I would call this a 2x3 system. Two equations, that's the first number, 3 unknowns. We would call this an underdetermined system. There are more variables than there are equations. So the previous examples of 2x2, 3x3, we have the same number of variables as you do equations. Those are the systems we like. Systems like these, where you have more variables than you have equations, you can kind of think of each equation as a constraint, as a limiting factor. And you can think of each variable as a degree of freedom. So if you want your system to have a unique solution, it is necessary that you have the same number of equations as you have variables, unknowns. All right, real quick, just so we can say we showed you one nonlinear system. Certainly, these are nonlinear. Nonlinear systems. I would still refer to the first as a 2x2. It's just a nonlinear system, so I don't really even care about classifying it. They're both 2x2s. They're both nonlinear. The first guy is nonlinear because of that first equation. This is a nonlinear equation. It's the equation of a circle, right? You know this, x squared plus y squared equals some constant. That's the equation of a circle. This guy and this guy are nonlinear, right? The second one here, the second equation in the last system is a parabola. That's the same as y equals 1 minus x squared. This is the same as x equals 2 to the y. So this would look like y equals the base 2 log of x. And this would be a parabola. Not pretty, these systems. We can solve these sometimes. But not usually. For example, that second system, I suspect I would have a very hard time solving. But the first system, I could solve. It's not terribly bad. Linear systems, on the other hand, are totally understood. When solutions exist, sometimes they don't. When solutions to linear systems exist, we can always find them. And when I say we here, I don't just mean like you and me, I mean like mathematicians in general. So mathematicians in general can't solve nonlinear systems. Okay, it just turns out to be the case that the mathematical machinery running underneath them is such that there's no nice way to solve most of them. You can approximate solutions using computers, but solving them exactly by hand, out the window for 99% of nonlinear systems. Linear systems, on the other hand, are extremely nice. We will see that every linear system lives in one of three categories. Either there is no solution, there is a unique solution, meaning a single value for each variable that makes the system happy, or there's infinitely many solutions. And for linear systems, we can tell when there are no solutions. We can tell when there is one solution and we can find it. And we can tell when there are infinitely many solutions, and we can categorize or classify those infinitely many solutions. We can characterize them, is the word I was looking for. Describe them. There's several methods. So we don't really care about these. These are hard, right? We're not going to mess with these. With nonlinear. But for linear systems, boy, are we ever going to do it. I'm going to show you all the tools for solving linear systems. I'm going to start off gently with the stuff you've seen in grade school. First and silliest, we can solve them graphically. I'll elaborate on what this means, but basically you look for the point where the graphs touch. And for a 2x2 linear system, that means looking for the point where the two lines touch. For a 3x3 linear system, that means looking for the point where three planes intersect. For a 4x4 system, that means looking for the unique point in four-dimensional space where the hyperplanes all intersect. Going to have a hard time drawing that last one. In fact, going to have a hard time drawing the three-dimensional case also. So solving graphically really only works for 2x2s, and it really only works when the solution is so nice that you can tell by looking at the graph what point that is. In other words, this is kind of shitty. Moving down the shittiness scale to the less shitty method, you can solve them using substitution. This is where you solve one equation for one variable and plug that into the other equation. for other equations, then try to solve for that other variable. Okay, what's nice about substitution is that in a 2x2 system, it's pretty quick and easy. If you only have two equations and two unknowns, then you solve the first equation for x and then plug that into the second equation. That equation will now not have any x's in it, it'll just have y's. You can solve that equation for y and then back substitute to find x. This works, again, pretty well for 2x2s. But if you have a 3x3 system with three equations and three variables, then this becomes quite messy. If you're clever, you can use one round of substitution to turn a 3x3 into a 2x2. And then you can do further substitution to solve that 2x2 and then chase your way all the way back up, back substituting to find the values of all three variables. But it's messy. Really, you should only ever consider using substitution for 2x2s. Of course, this doesn't require that the solutions be super nice. Substitution will detect non-integer solutions, for example, but it's messy and it doesn't generalize well. So the big thing that we're going to learn here, and I'll tell you this right now, you will not be able to pass this last exam, exam 4. You will not be able to pass exam 4 unless you learn how to use elimination. All right, this is the Mac Daddy. This is the main tool. And this is what we're going to generalize with matrices. So if you don't learn elimination now, you're not going to be able to understand what's going on with matrices. I know everybody learned substitution in grade school, and I know we all like it because it's something that we're comfortable with. But this wouldn't be a math class if I wasn't asking you to learn something new. If you already know elimination, that's awesome. We're going to practice it a lot. So elimination is where you perform what are called row operations. To eliminate variables until you can read off the solution. So elimination is incredibly nice. First, the result of performing these row ops and running the elimination algorithm is a system of linear equations that says like x equals 1, y equals 7, z equals 0. Just straight up, there's your answer. Other nice things here, this works great on 2x2s. It also works great on 3x3s and 4x4s and 10x10s. This works good on infinite dimensional systems of equations, whereas these things fail massively on anything larger than a 2x2. So yeah, elimination, that's going to be the game. Now, before we do that, I'm going to show you one example of each of these, because I have to. And we'll stick to 2x2s for now. So yeah, let's do it. Real quick, let me annotate. This is terrible. This is like okay for 2x2s, and this is the main tool. It's good. All right. I will look at a graphical solution really quickly. And then we'll solve that same system by substitution. And then from that point on, I will use elimination for everything. All right, here we go. So let's solve the linear system. 6x. 6x minus 2y equals 0, and 5x plus 2y equals 22. Oop, we can't see that at all. There we go. Focus. All right. This is a linear system because both equations are linear equations. It's a 2x2 system because I have two equations and each equation has two variables. If we're going to solve this graphically, what that means is I need to graph both of those equations and look for the point where those graphs touch. I will show you how to solve this by substitution, just in case you haven't seen or you need a refresher. But then, like I said, most of the time we're going to use elimination. So it's just a warm up. Graphical solution. Well, let's take that first equation, 6x minus 2y equals 0. See if we can graph it. If I add 2y to both sides, and then divide both sides by 2, I get 3x equals y, or y equals 3x, which is a line through the origin with slope 3. Okay, so 7, 6, 5, 4, 3, 2, 1, 1, 2, 3. So if I want to graph this line, I would say, okay, it's a line through the origin, the y-intercept is 0, and the slope is 3. So we're going to go through 1, 3 here. And maybe I'll graph this guy in purple. Something like this. I'll have the point 2, 6 on there. 0, 0, 1, 3. You get the idea. The other one, 5x plus 2y equals 22. Let me put him in color. I put down 2y, yeah. Well, if I subtract 5x from both sides, I get 2y equals negative 5x plus 22. And then I can divide both sides by 2. I get y equals negative 5 halves x plus 11. So this is a line with slope negative 5 over 2 and y-intercept 11, which would be like way up here. I can find where this thing is 0 by setting this equal to 0, and I would get, let's see, 22 fifths. So it's a slightly weird looking thing. Let me call this up here. Okay, 9, 10, 11. And that slope is negative 5 over 2. That means if I go over 2, I go down 5. So the line that we're going to get here, roughly looking like this. And we can see from the picture that these two lines, they do cross. Looks like they cross somewhere around here, around 2, 6. So x equals 2, y equals 6 might be our solution. I'll say would appear to be our solution. You can see the limitations of this method, right? I'm really guessing at this ordered pair here. I had to graph both of these and then just try to tell where they cross. On the other hand, if I solve this by substitution, I can get the exact solution, no guesswork. (6x minus 2y equals 0). 5x plus 2y equals 22. I'm going to solve the first equation for y. So I've actually already done that over here. I know that y is equal to 3x. Then I plug this in, or substitute, that's the term. Into the other equation. And I want to emphasize the word other there. If you plug this thing into the first equation, you're just going to get 0 equals 0, which is really not helpful. So when you're solving by substitution, solve one of the equations for one of the variables. Doesn't matter which equation or which variable. Solve one of the equations for one of the variables, then plug that into the other equation. So that means 5x plus 2y equals 22 will become 5x plus 2 times y, which is 3x, equals 22. And you see now there are no more y's in this equation, just x's. So I can solve this thing. This is 5x plus 6x equals 22, which is 11x equals 22. So x is equal to 22 divided by 11, which is 2. And then we're going to take this. So this was our first step, solve one of the equations from the variables. This is the second step. Plug that into the other equation, then you solve that other equation. And then the very last thing we need to do is take this x equals 2 and plug it back into either of the original equations to get y. So if I take this x equals 2 and I plug it into 6x minus 2y equals 0, that gives me 6 times 2 minus 2 times y equals 0, which means 12 minus 2y equals 0. So 12 equals 2y, which means 6 equals y. So you get your solution here. X equals 2, y equals 6. Which is what we thought we were getting graphically. All right, and just to be clear, both of these methods are kind of crappy. Questions on either of these? Okay. One more attempt to solve graphically. Okay. So let me try to graph both of these equations. If I take 8x minus 2y equals 5 and try to put this into my y equals mx plus b, I can subtract the 8x over, I get negative 2y equals negative 8x plus 5. And then I can divide both sides by negative 2, and I get y equals 8 divided by negative 2. Sorry, negative 8 divided by negative 2, that's 4x, and then negative 5 times. Do the same thing with the other guy. Got negative 12x plus 3y equals 7. So that's 3y equals 12x plus 7. And then dividing both sides by 3, I get y equals 4x plus 7/3. What do you notice about these two linear equations here now that they're in this form?
They have the same slope.
Yeah, they have the same slope. What do we call lines that have the same slope? What's the word for that?
Parallel.
Very good, they're parallel. So these are parallel lines. And for the system, that's bad news. Because parallel lines don't intersect. Okay, so negative 5 over 2, that's negative 2.5. So 1, 2, 3, here's his y-intercept. Positive 7/3, that's positive 2 1/3. Here's 1, 2, 3. Both of these have slope 4. So that first line looks something like this. And that second line, 7 over 3, yeah, 2 1/3. Looks like this. And these parallel lines, they'll never touch. Means the system has no solution. These distinct parallel lines will never touch. So this system has no solution. If we tried to solve these by substitution, say I took this expression 4x plus 7/3 and I plugged it in here, then I would get a contradiction. I would get something like 2 = 0, which would also tell me that there is no solution. I think rather than going through that, I don't, because substitution is such a waste of time, I don't think it's worth actually running through another example here. But I do want to describe to you the cases here. So just by graphing these, by realizing that they are parallel lines with different y-intercepts, they're never going to touch. This is a theorem. All linear systems fall into one of the following categories. And this is not just for 2x2s, 3x3s, 4x4s, 10x10s. It's possible that there is no solution, like the system above. It's possible that there is a unique solution, like the previous problem. X = 2, y = 6, that was a unique solution. One value for each variable that satisfies all the equations at the same time. The case we haven't seen yet, it's possible that there are infinitely many solutions. So these are the three possibilities for a system. That first picture, the no solution thing, always looks like this, parallel lines that are not touching. The unique solution case always looks like the picture we drew on the first problem. You've got two lines with different slopes, so they will touch at one and only one point. The infinitely many solutions case, this means that the two lines are sitting right on top of each other, if you're talking about a 2x2. Or if you're talking about a 3x3, it means that the planes intersect in at least one line, perhaps more. But the important thing I need you to remember from this theorem is really just that every system falls into one of these three categories. Either there's no solution, there's a unique solution, or there are infinitely many solutions. And in the infinitely many solutions case, we need to know how to describe those infinitely many solutions. We'll get there. But for now, I just want to show you how to solve some stuff with elimination. So, in case you haven't seen it before, we're going to solve 3x plus 2y = 14 and x minus 2y = 2 by elimination. So remember what elimination means. It means you're going to do some operations to the rows. And hopefully those operations will allow you to get rid of one of the variables. One of the things you're allowed to do.
I have a question.
Yeah.
Would x = 8?
Maybe. Let's see, I'm not sure. I don't know. Let's solve it and find out. So real quick, elimination. The operations you're allowed to do are multiply a row aka equation, right? One of the rows, by a non-zero number. You can add two rows. And then the kind of Mac Daddy is combining these. You can add a multiple of one row equation to another. These are the three operations. These are the operations you're allowed to do to try and eliminate one of the variables. So here's what I see. I see a 3x here and a 1x here. So I could multiply this second equation by -3 and add it to the first equation. That would make the x's go away because 3x plus -3x would be 0x. But that's not necessary here. See, I've got a 2y and a -2y. Those are already negatives of each other. So if I just add the first equation to the second equation, then I'll get rid of the y's. So that's the simple move here. Let's add rows 1 and 2. Some people write this like this. I'll show you. Let me just add. So 3x plus x would be 4x, 2y plus -2y would be 0y, and 14 plus 2 would be 16. So it looks like x is going to be 4 here. All right, because this has no y's in it. This just says 4x equals 16. So then x is 16 over 4, which is 4. So what I did here, adding rows 1 and 2, is eliminate the variable y. Eliminating the variable y gave me an equation which I could solve for x. And then I can back substitute this. Now use x equals 4 in either original equation to find y. This guy appears a little simpler, so x minus 2y equals 2 becomes 4 minus 2y equals 2. Subtracting 4 from both sides, I get -2y equals 2 minus 4 is -2. And then 2 divided by -2 divided by -2 is 1. So the solution here is x equals 4, y equals 1, or the ordered pair. Sometimes we do like to write our solutions as ordered pairs because geometrically that's what they are, 4, 1. Any questions about what we did here? Okay. Let's get some more practice. Let's solve 3x minus 3y equals 8 and 3x plus 3y equals 16 by elimination. Again, if I just add the rows, the y's will go away. All right, negative 3y plus positive 3y. Here I'll get 3x plus 3x, which is 6x. Negative 3y plus positive 3y, which is 0y. And 8 plus 16, which is 24. If 6x equals 24, that means y, sorry, 6y, no, that's correct, 6x equals 24. That means x has to be 4. Then if I back substitute this into either original equation, I can solve for y. Let's plug this into the second equation. Could use either original equation, doesn't matter. So the 3 times 4 plus 3y equals 16, which means 12 plus 3y equals 16, which means 3y equals 16 minus 12, which is 4. So y is 4 over 3. And certainly it's possible that your solutions are not whole numbers. This will happen a lot. As these problems get more and more complicated, we certainly will have to deal with fractions. We'll have to do quite a bit of fraction arithmetic. It's not anything to be afraid of. So we could say i.e. our solution is the ordered pair 4, 4/3. Or you could just say x equals 4, y equals 4/3. I don't care. So these are two very simple, very straightforward elimination problems. Each of them had a unique solution, right? A single ordered pair, a single value for each variable that made both equations true at the same time. Let's revisit the system we saw earlier with no solution and see what happens if we try to attack it with elimination. Recall that, what was it? 8x minus 2y equals 5 and negative 12x plus 3y equals 7 has no solution. Try to solve by elimination. All right. Well, here, I don't have like negative 2y and positive 2y. It's not as nice as the other one was. First observation, right? Eliminating either variable here is going to be a little bit more work than either of the two examples we've just seen. What can we do? Let me call this top equation equation 1. And let me call this equation equation 2. So I have a name for them, I can refer to them. Remember the operations I'm allowed to use. I'm allowed to multiply through a row by any non-zero constant. I'm allowed to add 2 rows, and I'm allowed to add a multiple of 1 row to another row. I would like to make like this a 8x and this a negative 8x if I could, or make this a negative 2y, make those match up so that I can add them and have one of the variables go away. I could multiply through equation 2 by 1/3. So the first equation will stay the same, 8x minus 2y equals 5. And when I multiply through this row by 1/3, 1/3 times negative 12 is negative 4x. 1/3 times 3y is just y. 1/3 times 7 is 7/3. And here, show up some fractions. You just have to deal with them. Okay. Well, now it's getting closer to being able to eliminate, right? I've got a negative 2y here and a positive 2y here, so I could multiply through this second equation by 2, and that would give me the ability to eliminate the y's. Let's go ahead and do that. Or I could multiply through this first equation by 1/2. That would give me the ability to eliminate, ooh, looks like either the x's or the y's. Let's do that. Let's multiply equation 1 by 1/2. That means equation 2 is going to stay the same. Negative 4x plus y equals 7/3. And if I multiply through this guy by 1/2, I get positive 4x minus y equals 5/2. Well, this is interesting. Because now if I add these equations to each other, the x's go away, but also the y's go away. Let's see what we get. Let's add equation 1 to equation 2. I'd have 4x minus y equals 5/2. And negative 4x plus y equals 7/3. And if I add these up, I get 0x plus 0y equals 5/2 plus 7/3, whatever that is. Okay, so we got to figure this out. Common denominator over here is going to be 6. That's 15/6 plus 14/6 is 29/6. So I get 0x plus 0y equals 29/6. Something is very wrong with this. What is 0x?
No slope.
Well, just algebraically, if I gave you an equation and you had a 0x in it, you would just replace that by 0, right? 0 times anything is 0.
No solution, right?
Yeah, this just says 0 equals 29/6, which is a contradiction. Zero is not equal to 29/6. That's a lie. So when you run through your elimination process, you arrive at a contradiction. which means the system has no solution. So kind of the way elimination works, you assume that a solution exists, run through this procedure to find the solution. Well, if there is no solution, then you're going to arrive at a contradiction because your assumption that a solution existed was incorrect. So this is what it looks like when you eliminate and the system you're working with doesn't have a solution. You get a contradiction. Questions on this one? Okay. I'd like to do one more elimination problem here, where we have a solution, and then one more where things are a little weird. So let's solve, just getting practice with elimination. Solve 2x plus 5y equals 15 and 4x plus y equals 21 by elimination. So remember what we're doing. We're using these operations, multiply an equation by a constant, add two equations, add a multiple of one equation to another, to try and get rid of one of the variables. When I look at this, I see a 5y here and a y here. I see a 2x here and a 4x here. So I could eliminate the x's if I multiply through this first row by -2 and then add to the second row. Let's multiply through row 1 by -2. That will give me -4x minus 10y equals -30. And then the second row stays the same, positive 4x plus y equals 21. And now I can add rows 1 and 2. This time I'm not going to write out that thing. I'll just do the addition. So -4x plus 4x is 0x. That's what I wanted. -10y plus y is -9y. And -30 plus 21 is -9. And what does this say? Well, 0x is 0. This is just gone now. This is -9y equals -9. So dividing both sides by -9, we get y equals 1. And then I can back substitute this into any of these equations to find x. I think the easier equation to put this into is the second one. I'm doing this in equation 2. 4x plus 1 equals 21 means 4x equals 20. Which means, so subtract the 1 over, get 4x equals 20. then divide both sides by 4 and get x equals 5. So our solution is the ordered pair five, 1. X equals 5, y equals 1. Okay. Last example for the day. First questions on this. So here's our last example. Let's solve three x minus 6y equals 12. 4x minus 8y equals 16. And we'll call this equation 1 or row 1. This equation 2 or row 2. And we want to solve this by elimination. I can try to eliminate the x's or the y's, doesn't matter. There's no nice integer I can multiply through equation 1 to make 3x into 4x. I could multiply by 4/3 if I wanted, a bit of a hass. But let me hit each equation with something. So we'll do two of these things at once. Let's multiply equation 1 by 4 and equation 2 by 3. So equation 1 is going to become 12x minus 24y equals 12 times 4 is 48. And then multiplying equation 2 by 3, I get 12x minus 24y, right? 8 times 3 is 24. 16 times 3 is 30 plus 18 is 48. So now if I subtract the two equations or multiply equation 1 by -1 and add to equation 2, right, which is the same as subtracting row 1 from row 2, I'll get 0x plus 0y equals 0. Interesting, right? So if I multiply through this first equation by -1, it becomes -12x plus 24y equals -48. And if you add that to this, everything becomes 0. We do that, and then we add these guys, we get nada. 0x plus 0y, that's 0. So this says 0 equals 0. Is that a contradiction?
No.
No, it's not. 0 is equal to 0. What this means is there's infinitely many solutions. the word for this is a tautology. It's a statement, which is always true. Which means this system has infinitely many solutions. Now, that doesn't mean any numbers x and y solve the system. What it does mean is that you can plug in any number for x and find a corresponding number for y, which solves the system. So quick note. This does not mean any ordered pair x, y solves the system. What it does mean is that given any number x, we can find a corresponding y value such that x comma y solves the system. Right? Like 0, 0 doesn't solve the system. If you plug in 0 for x and 0 for y, this first equation would be 0 equals 12, which is not true. But if you want to choose x equals 0, you can find a y value that works. So if I choose x equals 0, then this becomes negative 6y equals 12. Okay, so y would have to be negative 2. So what do we do? Means that if we're given any x value, we can find the corresponding y value. Well, let's find that corresponding y value for a generic x value. Here's how you do this. You let x equal t be a generic x value. Right, a whatever x value, just call it t. And we find y in terms of this x value. Really what this means is that the two equations we started with were the same equation. So I can plug t in for x to either of the originals. And really what this means is that these two equations are really the same equation. So if I want to find the set of all solutions, I'm just going to plug in t for x into either one of these and solve in terms of y. I'll use the first equation. So that would be 3 times t minus 6y equals 12. Subtract 3t from both sides, you get negative 6y equals negative 3t plus 12. Divide both sides by negative 6. And you get y equals, I'll write it like this, negative 1/6 times negative 3t plus 12. In other words, y is equal to, now I distribute the negative 1/6. Negative 1/6 times negative 3t is 1/2 t. negative 1/6 times positive 12 is -2. So I let x equal t be a generic x value, and that means that the corresponding y value is 1/2 t minus 2, i.e. the solution is all ordered pairs of the form t, comma, 1/2 t minus 2, where t is any real number. Sorry, this is a nice final answer. So elimination is really nice. Elimination either arrives at a unique solution, in which case that is your solution, arrives at a contradiction, in which case you have no solution, or arrives at a tautology, which means you have infinitely many solutions. The only case where you have to do more work after that is if you get that tautology, if you have infinitely many solutions. What you do there is you just let x be t. Just let one of your variables be some generic parameter is the word. And then you solve for the other variables in terms of that parameter. So like I said, if you look at the original equation, 0 for x and y does not solve the system, right? If you plug in 0 for both x and y, you don't get a true statement in either equation, which means that not every ordered pair solves. But if you do want to find the solution to the system that corresponds with x equals 0, that would be 0, comma, 1/2 times 0 minus 2, or 0, comma, negative 2. There is a solution associated with t equals 1. That would be 1, comma, 1/2 minus 2, or 1, comma, negative 3/2. There's a solution associated with t equals 6. That would be 6, comma, 1/2 times 6 minus 2 is 1. There's infinitely many solutions to this system, and they are all of this form. All right, there will be problems on your last midterm. I promise you at least one, where you have to solve a system of equations using elimination, arrive at this tautology, and then write down the solution in full generality, meaning get to this. Next time, we're going to look at some bigger systems, 3x3 systems, 4x4s even, and then I'll show you how to rewrite them as matrices. Turns out these row operations that we're doing are, you don't need to write the variables. You can kind of just write the numbers. And that is a nicer way to solve these things. And that will lead to the study of what are called matrices and matrix algebra. And the last sort of things that we're going to really care about at the end of this semester is learning how to do algebra with matrices. And that is the beginning of this new field of mathematics we're entering called linear algebra. And I do hope that you enjoy it because it is quite beautiful. And it's probably the most useful area of mathematics. If you had to pick kind of one kind of math that like is important everywhere, it's not calculus. As important as calculus is and wonderful as calculus is, linear algebra is way more important. Yeah, there is a new homework set. I'm going to open up a fresh homework set for you guys today. It's going to have systems, right? So you'll be solving 2x2s, 3x3s. If the problem says solve by elimination, please solve by elimination. That's the main thing we need you to practice is getting comfortable with elimination. So I will be popping open a new homework set. Some of it will be 2x2 stuff that you can dive into right away. Some of it will be 3x3 and larger stuff that you can start on if you like. But you know, we haven't talked about those yet, so we will get to those on Wednesday. Alrighty, gang, that's it from me. I hope you have a lovely rest of your day, and I will see you next time. We do have class Wednesday. We do have class Wednesday. I know Thursday is Thanksgiving, but the college is not closed on Wednesday, so we do have class.